So one of the most important tools in our chapter 4 is the so-called singular value decomposition. Let's recall what that is. And let me start with the little diagram that I was drawing when introducing the operator norm. So you have your operator A from x to y. We will see that x and y will be Hilbert spaces, or at least Euclidean spaces, because we need scalar products. And you start with the unit circle in x, so the set of all vectors from x that have norm 1. Okay, if you apply the operator A to the elements of your unit circle, then you will find on the other side something like an ellipse that is also centered at 0. And we've been talking about the longest radius and the smallest radius of that ellipse when talking about bounded operators and operators that are bounded from below. Let me show you a little demo program here. And to be able to actually draw something in 2D here, we take an operator that takes R2 into R2, and therefore it can be represented by a 2x2 matrix. In this case, you see your matrix up here in this corner, and okay, on the left you see two vectors, a green and a blue vector in your x space, and on the right you see their images in the y space. Okay, now just follow the green vectors. So I'm taking the green vector on the left that has length 1, and I'm starting to rotate it around the unit circle. Ignore the blue vector for a moment. And while that green little vector is traveling around the unit circle, you can see its image, the other green vector on the other side, traveling around an ellipse. I think we all agree that very much looks like an ellipse. Okay. And now it's time to also take a look at the blue vector. So let me again rotate the green vector along that unit circle. And you can now see that the blue vector is running away from the green vector, always in a right angle. So it's always 90 degrees before the green vector, if I rotate like that. On the other side, where blue and green are running around the ellipse, you have surely spotted already that they are not always in a 90-degree angle, one from another. Sometimes it's bigger, like now, and sometimes it's smaller, like now, but at some point in between you get a right angle, maybe now. And the interesting thing is that you observe this right angle when the blue and green line on the ellipse mark the longest and the smallest radius. Should we try again? So we continue this for a little bit, and the next time they are orthogonal is about now. And again they mark the longest and the shortest radius of our ellipse. Okay, so let's draw the longest and the shortest radius of our ellipse here. And let's pretend the original points on the x side that correspond to this red and blue vector here, or maybe the red and blue vector on the other side. And let me draw them in a right angle, one from another, because that's what we observed. Let me label these vectors here as v1 and v2. so that on the other side we have a v1 and a v2. And now let's split the map from x to y, that is given by a, into three much simpler steps, and these are the following. At first you rotate your unit circle in x so that your red and blue vector become the canonical unit vectors that go in coordinate directions, and let me denote them by the usual E1 and E2. And then you take that circle and stretch the whole plane with the circle on it in axial direction, but you use different stretching factors for every axis. And in our case, you stretch in the horizontal direction, maybe with a factor of 2, while in the vertical direction, your stretching factor is maybe just 0.5, so in fact you're shrinking. But that will turn your circle into an ellipse that already has the right radii, except that it needs another little rotation before it looks like our ellipse that the matrix A produces from the unit circle as its input. Okay, these little stretching factors down here that I made up to be 2.5 are typically called S1 and S2, where S is not for stretching, but instead for singular value. Okay, but then we know what we have to put here and here. E1 is stretched by this factor, and E2 is stretched by that factor. And then you call the unit vector in this direction here U1, so that the total vector here becomes S1 times U1, because we know its length is S1 and it just got rotated. And similarly, you call the unit vector in that direction U2, so that this is just a scaled version of U2, and the scaling is S2, because that's the length of this blue vector here. Okay, now let's try to figure out matrices that do these jobs. And let's start with this stretching here, which is pretty simple. Here, of course, you use a diagonal matrix, which has S1 in the first diagonal entry and S2 in the second diagonal entry. And the matrix is typically denoted by a sigma, which is the Greek capital S. Of course, not to be confused with the sign for summation. Okay, this rotation here is much easier to understand if you look at it in the other direction. Let's do that first. Of course, that is also a rotation, and it's a rotation that turns the canonical basis vector E1 into V1 and E2 into V2. And if you want to write down the matrix representation for that rotation, all you have to do is in the first column, you put the image of your first basis vector under the rotation, which is V1. And in the second column, you put the image of your second basis vector under the rotation, which is V2. Let's abbreviate this matrix by a capital V. Now, because its columns are orthogonal to one another and have length 1, this is an orthogonal matrix, which means its inverse is just its transpose, or let's say its adjoint if we are complex valued. So for this direction here, of course, we have to take the inverse of V, But like we just said, that is the adjoint of V. And it remains to write down the matrix for this rotation here. And to do so, let's forget about the stretchings S1 and S2 for a moment. So let's pretend we still have a circle here with E1 and E2 as the horizontal and vertical vector. And then we would have a circle here with U1 and U2 as their corresponding images. So the first column of this rotation is just the image of E1, which is U1, and the second column is just the image of E2, which is U2. And let's abbreviate that matrix by a capital U. Okay, so the essence of that diagram is to say that instead of taking the operator A here directly from X to Y, which in our cases is R2 and R2, we could take this rotation V star, followed by that stretching sigma, followed by that other rotation U. Okay, and this exactly gives us this equality here, where of course we recall that we have to read these products from the right to the left.